Hello everyone, my name is Brant Kedrowski, and this organic chemistry lab video covers an organic structure drawing and modeling experiment, part 3. In this section, we're going to be dealing with isomers of carbon-carbon double bonds. So this question asks you to build the two compounds shown below. They're both alkenes. Use carbon atoms with 4 holes and 2 curved bonds from your model kit to construct each one of the carbon-carbon double bonds, and your structure should look like the pictures below. I've gone ahead and built models of these molecules to demonstrate their behavior. One of the really important features of the carbon-carbon double bond is that it is rigid. The pi bond of the carbon-carbon double bond prevents rotation. This was described in a previous video on model kit use, so you should definitely check that one out if you haven't already done so. I'm going to pick up the left structure here and attempt to rotate about the central carbon-carbon double bond. You'll notice the model kit isn't going to let me do that. This is an accurate reflection of the CC double bond. It is rigid. The situation is the same with the right structure. It's also rigid about its central carbon-carbon double bond. Due to the rigidity of the carbon-carbon double bond, it's not possible to rotate one of these structures and make it look like the other one. No matter what you do, these are always going to be unique structures. They are non-superimposable. No matter how you rotate these molecules, you'll never get all the groups to line up at the same time. There'll always be problems with CH3s and hydrogens not matching. These molecules are clearly different, but how are they different? They're not connected differently. Each of these has a 4-carbon chain with a CC double bond in the middle. The difference lies in the direction that their groups point in 3-dimensional space. Imagine bisecting each one of the carbon-carbon double bonds lengthwise as indicated by the dotted lines in the diagrams. The structure on the left has its CH3 groups on opposite sides of that dotted line. We call this arrangement trans. The structure on the right has the 2 CH3 groups on the same side of the dotted line. We call this arrangement cis. These two molecules are different in the directions that their groups point in 3-dimensional space. This is a new type of isomer that we've not seen before. This is called a stereoisomer. This next slide defines 2 different isomer types. First, there are constitutional isomers. These are also called structural isomers. These have the same molecular formula, but different atom connectivity. For example, here are 2 constitutional isomers of butane. They both have formula C4H10, but they're connected differently. We have a 4-carbon chain on the left and a 3-carbon chain with a branch on the right. These are connected differently. These are constitutional isomers. Then there are stereoisomers. These have the same molecular formula and the same atom connectivity, but they have different orientation of their groups in 3-dimensional space. For example, we have the 2 alkene species that we saw in the previous slide. These both have formula C4H8, and they have the same connectivity, but they have different orientations of their CH3 groups and CH groups in space. Here we're going to get into the next problem in the lab. Question 6 asks, in addition to the 2 molecules on the previous page, there are 4 other constitutional isomers with formula C4H8. Draw all 4 of these below. 2 of the molecules contain a double bond, the other 2 each contain a ring. So to refresh your memory, I'm going to put back up the structures of the molecules from the previous page, the 2 alkene stereoisomers. In addition to these 2, there are 4 other constitutional isomers. These are connectivity isomers, and it's your job to find those. You can draw them in either Lewis structure form or skeletal structure form. Just make sure they're drawn correctly. All your carbons should be making 4 bonds. I'll give you a couple of hints. First, we know we're going to be looking for 2 isomers that contain carbon-carbon double bonds. So just pre-build the CC double bond and then attach 2 more carbons in a way that doesn't duplicate the top 2 structures. To find the isomers that contain rings, I suggest the following strategy. Put 4 carbons out in front of you and try to find ways to arrange them to give 2 different connectivity patterns. I'm avoiding actually plugging in the bonds to the atoms in these models because the rings are very small and they're very strained. If you try to build a 3-membered ring or 4-membered ring, a triangle or a square with your model kit, you actually might break it. So you should try to avoid that. 3- and 4-membered rings in organic chemistry do exist and they're actually pretty common. But they are high energy and there's a lot of strain because the bond angles are compressed from the ideal of 109.5 in a sp3 hybridized carbon. Question 7 is pretty straightforward. It just asks you to draw 2 unique constitutional isomers that have formula C3H7Cl. It might be helpful to get your model kit out and use 3 carbons, 1 chlorine, and 7 hydrogens to help you do this. Just make sure that you have 2 structures that aren't the same, that are not superimposable. Finally, we have question 8. This asks you to build 2 models of the 2 molecules shown below and set them next to each other as I've shown in this diagram. Here we're representing bromine with a red atom, and those bonds are on wedges. We're representing the blue and the green as being fluorine and chlorine, and we have the hydrogen as a white atom. If your model kit doesn't contain enough green atoms, for example, you can use a different color like gray, for example. The idea here is build the models, make sure that you have them built right, and then see if you can superimpose them. Try to rotate one and superimpose it on the other. You really should go through the exercise to build the model and actually try to superimpose them rather than just trying to eyeball it. Then you decide whether these are the same molecule, whether they're constitutional isomers, or whether they're stereoisomers. This gets at an interesting thing that happens in carbon molecules that contain carbons that have 4 different groups attached. These are called stereogenic centers, and this is going to be the focus of a lot of what we do in organic chemistry to try to understand the shapes of molecules that have this particular feature. Question B asks you to replace the bromine atom and its bond in each model with a hydrogen atom, white, and a pink short bond, and then examine the two models and try to superimpose them. Can you do that now? And if you can, are they the same? Are they constitutional isomers, or are they stereoisomers? That's all for this lab experiment. I hope you enjoyed it, and I hope you learned something. There'll be more like it coming up, so stay tuned to this YouTube channel or subscribe if you'd like to learn more. If you found this video useful, check out the next one in the series or watch the prior video. And consider subscribing to my YouTube channel. My name is Brant Kudrowski. Thanks for watching.